This video is for section 9.1, and this is related to discontinuities and vertical asymptotes. So first of all, we need to talk about what a rational function looks like. So a rational function is simply one that has fractions. So we'll say it has fractions. Now, when we say has fractions, we don't just mean like 1/2 or 1/4, because you might have the equation y equals 1/4 x plus 2. That function has fractions, but that's not a rational function. In fact, isn't that a linear equation? Because it looks like an mx plus b. So when we say fractions, so I'm going to put kind of an x through that, that's not what we're talking about. When we say it has fractions, we're talking about maybe y equals x plus 2 over x minus 1. A fraction where you have variables in both the top and the bottom. I guess that you could have variables maybe in just the bottom, maybe 4 over x plus 2 might be another example of a rational function. But essentially you have variables either in both the numerator and denominator or just in the denominator. Okay, so that's what we mean by rational functions. So in general, we would say that polynomial functions are always continuous, meaning think about a polynomial, like think about a parabola. If I were to think about the graph of a parabola, right, it might look something like this. Well, there aren't any holes or breaks in the graph. If you start on the left side, you can draw all the way to the right and you don't have to pick up your pencil, right? It's continuous. But rational functions are different because rational functions are not always continuous. Okay? They are not always continuous. If you were to look down at example 1 and you look at that graph, that's a crazy looking graph. Like it has a hole right over here, and then right here at x equals 1, you can kind of see right in here there's this break in the graph. Over here at x equals 3, there's this weird break in the graph, okay? So polynomial functions could have rational functions could have any of that weird kind of stuff going on. Okay, so what does it mean when we say discontinuities, okay? Discontinuities meaning not continuous. Well, if I never gave you a math definition of continuity or continuous, and you would just know what you know about the English language and the word continuous, if you were to look at this graph right here in example 1, you'd say, no, that's not continuous because, for example, this part of the graph, let me put a different color, sorry. This part of the graph doesn't meet up with this part of the graph because there's like this weird random hole in the middle. Or you could say, well, obviously this graph is not continuous right in here because it comes this direction and then it stops, and then it picks up again up here, but those are not connected, right? They're not continuous, not connected. So that's the idea when you're just thinking about what it looks like on a graph to be not continuous. But essentially there's 3 things that could happen when we say that there's a discontinuity, okay? So number 1, there might be a hole in the graph, hole on graph. And when I draw a graph on paper, to show a hole, I put this kind of open circle. But if this were a calculator and you were looking at this graph, it wouldn't show an open circle. It would just show, now look what I do right here, it would just show like this space. Do you see where I drew it? It would just show this little space right there. And what that means is there's a hole, there's a space in the graph between those 2 sides. So that's what we mean when we say a hole. Another thing that might happen is you might have a thing where right here at x equals 1, where the left side does not meet up with the right side. Okay, so left does not meet the right side. Okay, and that's what I'm talking about down here in this second scenario. The left side over here is just this horizontal line. It does not connect. Maybe we say left does not connect to the right, okay? And then the final thing that can happen is you might have a vertical asymptote. Vertical asymptote. Now, we talked about vertical asymptotes, not very much, but a little bit when we were doing the parent functions, when we were graphing the parent functions. Remember the equation y equals 1 over x, and how we said the parent function is you've got this piece up here, and you've got this piece over here. And we said that right here on the y-axis, there's this imaginary line that the graph doesn't cross. That's called a vertical asymptote. At that time, we also talked about this line right here is like a vertical line that the graph doesn't cross, and that's called a horizontal asymptote. Well, today we're going to focus in on vertical asymptotes, and then in the next class, we'll talk more about the idea of horizontal asymptotes. So if you look down here at example 1, do you see that right here where x equals 3, there's this imaginary line that goes down, and the graph on either side does not touch that line. So that would be a vertical asymptote. Okay, so letter A. For what value of x is f of x not continuous? Well, when you look at this graph, start at the left. I just start working my way over. My eyes follow the graph. I start working my way over to the right, and when I get right here to where x equals -4, I see there's a hole. So we would say the graph is not continuous when x equals -4. Okay, well, if I keep going, I follow along this graph, I keep going along here, I head right here, and then right there at x equals 1, where the left side does not meet up with the right side, we'd say the graph is not continuous. And then finally, right here where we saw a vertical asymptote at x equals 3, we would say the graph is not continuous. So those are all places where the graph is not connected. Okay, let's talk about on what intervals is this graph increasing. Okay, so when is this graph increasing? Well, we always read a graph from left to right. Okay, so if I read this graph from left to right, increasing means going up, right? So I hop on the curve right over here, and would you agree that when I first start on this graph, it's going up, it's increasing. So I would say starting at -5, this graph is increasing. When it gets to this -4 piece, that's not, there's a hole there, right? So I can't say all the way from -5 to -3 because I need to make sure that we understand there's nothing going on there at -4. So I'm going to say from -5 to -4. And then the graph stops and there's a little space, but then it picks up again right here on the other side of -4, and it's increasing until I get to right there at -3. So I would say from -4 to -3. And the fact that I have a parenthesis on each side of -4 means the first piece goes until I get really close to -4, and then I pick up my pencil, and then I start again right after -4, and I go all the way to where x equals -3. So all in there, all of this in here is increasing. If I keep going, now my graph is going down, so I'm decreasing. Right here, it's constant, so it's not increasing or, oh, look what I was doing, you guys. It says on what intervals is f of x decreasing, and I was listing the increasing. So let's just change this to say increasing. Sorry about that. Increasing means going up, right? Okay, so I'm going down and then I become constant. Notice right over here, it's still going down, so it's decreasing. When you come up here, again, you always read left to right, so right in here, it's going down, so it's still decreasing. So the only times it's increasing are on those two pieces I mentioned. Why don't we, so that was the increasing. Why don't we list where it's decreasing? Okay, so it doesn't start to decrease until I'm right here. So from -3 all the way until I get to here at -1, it's decreasing. But remember we said right in here it's constant, it's not decreasing. But then when I pick up right here at -1 and I continue, now don't say to -infinity, because remember intervals are x values. So from -1 until I get to that vertical asymptote, that graph is decreasing, right? So, I'm sorry, not -1. This one picks up at +1, doesn't it? I'll get this right, I'm sorry. So from 1 until I get to 3, that graph is decreasing. But then when you jump up here and you start at 3 isn't it still decreasing until you get all the way over here to 7? Okay. So when we talk about increasing and decreasing, it's not at a specific point, but it's a whole interval of space. Okay, and remember, intervals are always x values. All right, sketch the graph of the piecewise function on the graph provided. Well, we did a little bit of this before. Not a lot, but we did a little bit. Remember, piecewise means you have several pieces of a graph. So first we look at the first piece. Remember, f of x means y. So I have the piece y equals x, right? So I'm looking at the graph of y equals x. Well, if you remember your parent functions, y equals x is this line that goes right through the middle, right? That's the graph of y equals x. But I don't want all of that graph. I only want the part when x is less than -2. So go to where x is -2, see where that hits your graph, right in here. And if I only want the part where x is less than -2, less than means to the left. So I only want the part of that graph that's on the left of -2. So I don't want the entire line. I just want a small piece of the line. Now, how do I know if that point, that endpoint, should be a solid dot or if it should be an open circle? Well, remember, you look right here, it says x is less than or equal to, I'm sorry, it just says x is less than. Since there's no equal to, that means I want that to be like an open circle. So there's this open circle right there. Okay, that's the first piece. So now let's look at the second piece. We're looking at y equals -2. Well, y equals a constant. Isn't that just a horizontal line? So if I were to draw the entire horizontal line when y equals -2, it would go all the way across here. Okay? But I don't want the entire line. I only want the part when x is between -2 and 1. Okay, well, x equals -2 hits my horizontal line right here. X equals 1 hits my horizontal line right here. So I only want the part of that graph that is right there between those 2 points. I don't want the entire horizontal line. I just want that part between the two. So now let's think about if I should include my endpoints or not. Well, there's an equal to on the -2 side, so I'm going to keep that as a solid dot, and that solid dot is filling in what used to be an open circle. But on the other side, when x is 1, there is no equal to, so there should be like an open circle over on the x equals 1 side. Okay, and so now we look at the third equation, x squared minus 2. Isn't that a parabola that's been moved down 2? So if I have a parabola that's moved down 2, there's the vertex, and it's going to do something like that, right? My parabola moved down 2. All right, but what part of that parabola do I want? I want when x is greater than or equal to 1. So see where that parabola hits x equals 1 right here. And if I only want the part that's greater than 1, that means I want the part over here on the right side. So I would only keep the right side. That means I don't want the other side of the parabola. Now, do I want that little endpoint to be an open circle or filled in? Well, because it has the equal to, it's going to be a filled in circle. So this is the piecewise function. They don't all have to be connected. Sometimes the pieces connect and sometimes they don't. So letter A says, for what value of x is the function not continuous? Well, where is it not connected? Well, it's not connected at x equals 1. Okay, so that's what it means to identify places where a graph is not continuous, right? Not connected. Okay. So let's talk about the idea of vertical asymptotes. Well, remember we talked about the 1 over x graph, right? And we said we know what 1 over x looks like. You've got like one piece right here, one piece right here, and we talked a minute ago about how you have this imaginary line right here, that's a vertical asymptote. You have this imaginary line right here, that's a horizontal asymptote. Okay, so letter A. As x gets very close to 0 from the negative side, okay, so I'm coming in from the negative side, and I'm following on my graph, going close to where x equals 0. Here I am coming in on this side. What happens to the y values? Well, isn't this graph shooting straight down to negative infinity? So the y values are going to negative infinity. Okay? Well, the mathematical way of writing this is to say as x goes to 0, and then I'm going to put like a little negative sign, almost like an exponent. That means from the left. So as x goes towards 0 from the left, comma, the y's go to negative infinity. It's kind of a shorthand for saying the words I just said out loud. As x goes to 0 from the left, y's go to negative infinity. Well, looking at this graph, as x gets very close to 0 from the positive side, so here's where x is positive, right? So as this graph goes towards 0 from this direction, what happens to the y values? Don't they shoot up to positive infinity? So they go to positive infinity. So the mathematical way of saying that is as x goes towards 0 from the right, meaning from the positive side, the y's go toward positive infinity. Again, just some math shorthand for saying what's happening here around that vertical asymptote. Okay, now remember, they gave me the equation up here at the top. They said the equation of this graph is y equals 1 over x, right? And remember, y means f of x. So it's kind of like saying f of x equals 1 over x. Okay, so remember function notation. What is f of negative 3? Doesn't that mean plug in a negative 3 everywhere you see an x? So if I plug in a negative 3, won't I just have 1 over negative 3? Okay, function notation means you have an ordered pair. What that means is there's an ordered pair at negative 3 comma negative 1/3. Well, if I would go over here to where x is negative 3, say 1, 2, 3, the y value right there is negative 1/3. That's what that means when you have function notation. What about if I have f of 1/2? Well, if I plug a 1/2 in for x, I've got 1 over 1/2. So that's like saying what is 1 divided by 1/2. If you do the keep, change, flip thing, that's going to come out to equal 2. So that means my graph has the ordered pair. If x is 1/2, y is 2. So let's see. If x is 1/2, so right in here, the y value is 1, 2. Boop, right in there. Right, 1/2 comma 2. And then the last one here says, what if x is 0? Well, if you plug in a 0 for x, you're going to have 1 over 0. But remember, haven't we always said that's the big bad thing? So if the denominator is 0, we say it's undefined. So is there a specific point on the graph? No, there's not. In fact, what's happening on the graph at x equals 0? Isn't that when we had a vertical asymptote? Okay, so we've just come up with a big, important thing here. If the denominator is 0, you have a vertical asymptote, because isn't that what happened here? My denominator was 0. Okay, so look at this graph. Wasn't this the parent function 1 over x? Right, remember 1 over x, and it's going to be moved 2 units to the right. And so didn't we talk about, hey, you move the entire graph 2 units to the right, so it's like moving the y-axis 2 units to the right. And then the negative, doesn't that mean it's flipped over? So instead of having this piece up here and down here, won't this one flip across the x, this one flips across the x? So actually the negative in front, I'm just doing the transformations that we did way back in the day. So that means I'm going to be over here. Oops, that's just what I said. I'm going to be up here and down here, right? Because I had to flip it across the x. So all I did was graph my parent function. We did that back at the beginning of the semester. So looking at that graph, what is the vertical asymptote? Isn't it when x equals 2? Does that make sense based on what we said? Does that make the denominator equal 0? That works. Okay. So how do I read this? As x goes toward 2 from the left. As x goes towards 2. So here's the left side. As I go towards where x equals 2, from this side, what's happening with my y values? They're going towards positive infinity. but as x goes towards 2 from the right, so as I come in from the positive side, from the right, what happens to my y values? They're going to negative infinity. Okay? So, without graphing, find the vertical asymptote. Well, we just said, and let's write this down so we're clear, we just said vertical asymptote is when the denominator equals 0. So I don't need a graph to know where there's a vertical asymptote. When I look at letter A, if that denominator is 0, I have a vertical asymptote. Well, if you solve for x, doesn't that mean x would be negative 4? So my vertical asymptote is x equals negative 4. Well, look at letter B. What value of x would make that denominator equal 0? Wouldn't you have a vertical asymptote when x equals 5? Because that would make the denominator be 0. For letter C, what would make that denominator be 0? If x equals 3. Notice that negative out in front has nothing to do with whether or not the denominator is 0. Okay, so vertical asymptotes are easy to find. You just set the denominator equal to 0. See what makes the denominator equal 0. Okay, so look at this next section. It says use the graph. So don't worry about the equation. Just look at the graph to find the vertical asymptotes. Well, when I look at the first one, kind of zoom in here a little bit, where is my vertical asymptote? Doesn't it look like it's right here on this line? Doesn't that look where I have my vertical asymptote? And what is that value of x? That's x equals 2. X equals 2. Hey, does this fit with what we just said? Would that make the denominator equal 0? Sure would, wouldn't it? Okay, look at the second one. I see 2 vertical asymptotes. It looks like there's one right along here. Doesn't look like there's one right along here, but doesn't look like there's another one right along here. Can you see that? So I think the one on the left here is 1, 2, 3. X equals negative 3. And it seems like the one on the right here is positive 3. By the way, they don't always have to be the same number, positive and negative. Would that make this denominator equal 0? Well, think about it. Isn't x squared plus 9 the same as x plus 3 times x minus 3? So do you see that x could be either 3 or negative 3, and that denominator would be 0, right? Okay, and if I look at this graph, it looks like the vertical asymptote is somewhere here between 0 and negative 1, right? I'm going to guesstimate at negative 1/2. And then it looks like it's like right in the middle here of between 2 and 3, right? So 2.5 would be what, 5/2? Okay, does that fit? Will those numbers make the denominator equal 0? Yes. So you can have more than one vertical asymptote. That just means your denominator is going to have more than one place where it equals 0. All right. Boxes are important. So how do the vertical asymptotes compare to the denominators of each function? Well, remember we said vertical asymptotes are when the denominators equal 0. Big topic. If you get nothing else out of today, this is what you need to get. Okay, so if I want to find the vertical asymptotes, I don't need the graph. I just look at the denominator and see when it equals 0. Well, isn't it always easier to find zeros when it's in factored form? So let's put this denominator in factored form, right? Difference of squares, 2x plus 3, 2x minus 3. So what would make that denominator equal 0? Wouldn't it be when x is negative 3/2 and when x is positive 3/2? So that means I have 2 vertical asymptotes. Look at letter B. What would make that denominator be 0? Well, I don't know. Let's factor it. X plus 7, x minus, not 3, x minus 4. That'll give me positive 3 in the middle. So that means I have a vertical asymptote at x equals negative 7 and x equals 4. And then on the last one, let's put our denominator in factored form. Hey, notice there's a common factor. So first we take out the x. So 2x squared minus 3x minus 20. Let's see if that'll factor any further. 2x and x. I know I need a positive and a negative, right? And then to get 20, I think I'll go for 5 and 4, but don't I need the 5 over here with the 2 and the 4 over here with the x? So will that give me negative 3x in the middle? Sure it will. Do your outer inner, okay? So notice in this time, the denominator has 3 factors. Well, that means there are 3 vertical asymptotes. So I'm going to have a vertical asymptote when x equals 0. That's from that first one, that common factor. And then I have x equals negative 5 halves. So there's a vertical asymptote at negative 5 halves. And another one at 4. So my vertical asymptotes are those 3. Okay? So look at this one. You might be saying, all right, I got it. But let me show you something with this one. Let's change the entire thing into factored form, right? Both the top and the bottom. So I'm going to have f of x or y, same thing, equals, on the top, I've got, let's see, how about x plus 3, x minus 1. I think that'll give me positive 2 in the middle, right? And then in the denominator, if we factor that, how about x plus 2 and x minus 1? I think that'll work, right? And you can see what's going to happen here, can't you? The x minus 1's cancel. We did this kind of canceling way back when. And so what I really have here is just x plus 3 over x plus 2. Okay, so I'm going to go to letter C first of all. Okay, for letter C, what would you expect to happen when x equals negative 2? Well, isn't that going to make the denominator equal 0? Oh, but wait a minute. If the denominator is 0, doesn't that mean it's a vertical asymptote? So x equals negative 2, based on what we said a few minutes ago, is a vertical asymptote. Okay, so now let's go back to part B. What about x equals 1? Because that's what I would have gotten from that factor that canceled. So if it cancels out, is it still a vertical asymptote? That's what we're asking. If it cancels out, is it still a vertical asymptote? Well, let me answer that by showing you. If I were to put this in my calculator, notice this is the exact same equation that we were just talking about a minute ago, right? If I were to put this in my, and you don't need to do it, I'm just going to show you. If I were to put that in my calculator and just hit graph, it would look like this. So can you tell what's happening at 1? You can barely tell what's happening at 1. You can definitely tell that you have a vertical asymptote at negative 2, right? You can tell very obviously vertical asymptote at negative 2. But it's kind of hard to tell what's happening right there. So what if I show you a picture of it zoomed in? If I were to zoom in on it, look right here. If I were to zoom in on that spot, what you can actually see is there's this space in the graph. That's what we mean when we say there's a hole in the graph. So what happens at x equals 1? There is a hole. Well, what's the actual ordered pair for that hole, right? What's the y value? So it would be 1 comma, it looks like 2, let's guesstimate, 2 3/4-ish. So I'll say 2.75. So it looks like the hole is at 1 comma 2.75. Okay, so let's summarize. What did we say about vertical asymptotes? Vertical asymptotes are when the denominator equals 0. Okay, vertical asymptotes should always be written as the equation of a vertical line. Notice every time I gave an answer for a vertical asymptote, I wrote x equals. Now, I don't know if you did that, but like look up here at these A, B, and C. Notice I said x equals negative 3 halves, x equals 3 halves, x equals negative 7, x equals 4. I didn't just list the numbers. I always wrote it as x equals. Why? Because that's what the equation of a vertical line looks like, right? Don't all vertical lines have x equals some number? Okay. And then I just made a point. A graph is never going to cross the vertical asymptote. Okay, holes, they're not when the denominator necessarily equals 0, but those come from the factors that cancel. So that's when the canceled, okay, does canceled have 2 L's or 1? No, I don't know. I'm going to write canceled, and then I'm going to write another L kind of on top of that one. That way, if you think it's a 1, then it's 1. If you think it's 2, it's 2. Okay? It's when the canceled factors equal 0. So remember up here how the x minus 1 canceled, but when would that parenthesis have equaled 0? Wouldn't it have equaled 0 when x equals 1? Okay, that's what I mean by that. And then holes, because holes are a specific place that there would be a point, so we always write holes as an ordered pair. That's why up here when I said, hey, where's the hole, I wrote it as an ordered pair. Okay, so how does this work for homework, that kind of thing? Well, without graphing, so I don't need a calculator, find all holes and vertical asymptotes. So the first thing I need to do is factor it first. So on the top, I've got, let's see, x plus 3 and x minus 1. That'll give me the positive 2 in the middle, all over x minus 1. Okay, I can see that the x minus 1's cancel, and so my actual equation is y equals just x plus 3, right, because the 1's canceled. So because of the fact that it canceled, the x minus 1's canceled, that means there's a hole when x equals 1, right, because that's what would make that factored, that one that canceled, that's what would make that equal 0. But how do I find the y value for my hole if I don't have a graph? Well, if I know that x is 1, just plug 1 in place of x in your equation. If I put a 1 right there in place of x, then y is 1 plus 3, so the y value is 4. Okay, so that's my hole. On this one, are there any vertical asymptotes? Well, remember, vertical asymptotes are when the denominator is 0. Well, look right here. This is my simplified form, and there is no denominator. If there is no denominator, then there is no vertical asymptote. So if everything cancels out of the denominator, you don't have any vertical asymptotes. Okay, let's look at letter B. On this one, we start by putting them in factored form. So let's factor. I'm going to say y equals, I can't factor the top, but I can factor the bottom. Let's see, x plus 4, x minus 3. Will that work? That'll give me positive 1x in the middle. And so in this case, the x minus 3's cancel. And so what I have left is just, if everything cancels from the top, you have a 1, right? So 1 over x plus 4. Okay? So holes come from whatever cancels. So in this case, the x minus 3 canceled. So there's a hole at 3 comma something. If I want to know what the y value is, put that 3 in for x. If I put a 3 in for x, wouldn't I have 1 over 7? So the y value is 1 over 7. So that's where the hole would be on this graph. And then remember, vertical asymptotes come from when the denominator is 0. So what would make that x plus 4 equal 0? Wouldn't x have to equal negative 4? Okay. So holes on vertical asymptotes, you just factor and then look at the denominator. All right, let's try the last one here. If I put this in factored form, g of x is the same as y. I don't know why I'm writing y. So y equals, if I factor the top, let's see, how about x minus 3, x plus 1? Will that give me the negative 2 in the middle? I think that works. On the bottom, I'm going to have, what about x minus 3, x plus 2? I think that'll give me the negative 1. That works. Okay, I can see what cancels. So my simplified version is just x plus 1 over x plus 2, right? Okay, so what about my holes? Well, remember, holes come from what cancels. It was an x minus 3, so that means the x is going to be 3. How do I find the y? Again, just plug 3 in for your x value into that simplified version. So I'm going to have 3 plus 1 is 4 over 3 plus 2 is 5. So that's my ordered pair, 3 comma 4/5. And then my vertical asymptote, well, go to your simplified version. What would make that denominator be 0? Wouldn't it be when x equals negative 2? So I want to make a point. Notice every vertical asymptote I wrote in the form x equals when there was one. And every hole I gave the answer as an ordered pair. Okay? So what does this look like on the graph? Okay, let's look at letter A above. So for letter A above, there was no vertical asymptote. and there was a hole at 1, 4. So let's put on our hole at 1, 4, 1, 4. So there's a hole right here. Well, how do I know what the graph looks like? Look at the simplified version of the equation. The simplified version of the equation was right here, wasn't it? It was y equals x plus 3. So what would the graph of y equals x plus 3 look like? Isn't it just a line? I mean, think mx plus b. Isn't it a line that has a y-intercept of 3 and a slope of 1? And do you see that if it has a slope of 1, if I go up 1 over 1, isn't it going to hit that hole? Up 1 over 1. If I wanted to extend it the other direction, I could. So if I were to draw that line, in, it's going to be something like this. And keep in mind, we had said, hey, there's a hole right there at that point 1, 4. So I'm going to show the hole by putting a little open circle there. So that would be the graph of letter A. Okay, look at letter B. Well, letter B did have a vertical asymptote, didn't it, at -4? So let's put that on. So vertical asymptote at -4. And there's a hole at 3, 1/7. So 1, 2, 3, and 1/7 is just going to be barely above the x-axis right there. Okay, so how do I know what the graph is? Well, what was the simplified version of my equation? Well, the simplified version of my equation was y equals, remember it was right here, 1 over x plus 4. Hey, I know what that is. That's the 1 over x graph, isn't it? That's been moved 4 units to the left, which makes sense because there's my vertical asymptote. So if I were drawing in that graph, it's got this thing, right? Just make sure when you draw it, it's going to come down and hit right there where that hole is. And then isn't the other piece of a 1 over x graph over here? Right? Something like this. Hopefully you remember your parent functions. Okay? And then, oh, it doesn't have me graph letter C. Yeah, we won't worry about letter C. Okay? So for the homework, I just wanted to show you kind of what's happening with the graphs. For the homework, we won't focus on the graphs. For the homework, I would say go ahead and do, 1 through 4, just like we did A, B, and C up on the previous page. So these are just like example A, B, and C from page 97. You don't have to do any graphing. And then down here, I go ahead and find the vertical asymptote in the hole, just like we did those same examples up there, just like we did A, B, and C on page 97. Now, if you want to try and put it together like we did on the graph, then you can try and put it on the graph. Otherwise, we'll go over the graphing part of it in class next time. All right, hope that helps.